October 2015. Astronomers point the Kepler Space Telescope at an unremarkable F-type star 1,470 light-years away. Star designation KIC 8462852. Nothing special, just another data point in humanity's quest to find exoplanets. And then the data comes back. The star is flickering. No, not flickering, dimming by 22%, then back to normal, then dimming again, this time by 15%, then 8%. Random intervals, asymmetric patterns, nothing like anything we've ever seen. Dr. Tabitha Boyajian analyzes the light curves and does what any rational scientist does when confronted with data that makes no sense. She triple-checks the instruments. The instruments are fine. The star isn't. Within months, the scientific community has a problem because there are only so many things that can make a star dim by 22%. Planets don't do that. Even Jupiter would block maybe 1%. Dust clouds don't behave that irregularly. Comets? Maybe, but you'd need a swarm so massive it defies probability. And then, someone, because there's always someone, says the quiet part out loud. What if it's artificial? Welcome to Tabby's star, the most mysterious object in our galaxy, the star that made serious scientists start using phrases like alien megastructure in peer-reviewed papers, the star that launched 1,000 conspiracy theories and exactly 0 confirmed answers. Because here's the thing, we are actively searching for Dyson spheres, not as a joke, not as a thought experiment. Real telescopes, real budgets, real scientists looking for real alien megastructures that could be capturing the entire energy output of stars. And we found candidates, plural. Today we're talking about Dyson spheres, structures so vast they make the Death Star look like a beach ball, so expensive they'd cost more than every economy that has ever existed, and so advanced that finding one would mean we're sharing the galaxy with civilizations that could erase us without noticing. This is Dyson spheres, the $100 quintillion megastructures we're already searching for. I'm about to explain why the most important question in human history might not be, are we alone, but rather, are we being watched by something we couldn't comprehend even if we tried? Let's start with the simple question. What the hell is a Dyson sphere, and why would anyone build one?
Before we dive into the mystery, we need to understand what we're even talking about. Because Dyson sphere sounds like science fiction, and that's exactly what it was when physicist Freeman Dyson proposed it in 1960. Picture this. It's the Cold War. We're terrified of nuclear annihilation. We've just started the space age, and Freeman Dyson, a brilliant, eccentric physicist who worked on the atomic bomb and basically invented modern reactor theory, publishes a paper in Science magazine with the most casual title ever, Search for Artificial Stellar Sources of Infrared Radiation. The premise? Any advanced civilization will eventually run out of energy. Solar panels on a planet? Cute, but inefficient. Wind farms? Adorable. Nuclear reactors? Better, but you need fuel. Fusion? Now we're talking, but even fusion requires hydrogen, and planets have limited supplies. So Dyson asked, what if you just captured all of a star's energy? Not some of it, not most of it, all of it. A star like our Sun pumps out 3.8 times 10 to the 26th watts every single second. That's 380 septillion watts. To put that in perspective, all of human civilization, every light bulb, every car, every factory, every data center uses about 18 terawatts. That's 18 trillion watts. Our Sun produces 20 trillion times more energy than we use every single second, and 99.9% of it just radiates uselessly into empty space, wasted, lost, gone. Dyson looked at that cosmic wastefulness and thought a sufficiently advanced civilization would never tolerate that inefficiency. So he proposed the Dyson sphere, a megastructure that completely encloses a star, capturing 100% of its energy output. Build that, and you've essentially achieved post-scarcity. Unlimited energy means unlimited manufacturing, unlimited computation, unlimited everything. And here's where it gets interesting. Dyson wasn't suggesting a solid shell, because, and this is important, a solid shell around the sun would be physically impossible. Let me explain why, because this is where most science fiction gets it hilariously wrong. Imagine you build a solid shell around the sun at, let's say, 1 astronomical unit, about 93 million miles, roughly Earth's orbital distance. That shell would have a surface area of about 280 quadrillion square kilometers. You'd need to be, I don't know, maybe 100 meters thick to have structural integrity. Let's be conservative and say 10 meters. The volume of material required would be approximately 2.8 quintillion cubic kilometers. That's more mass than exists in all the planets combined. You'd have to disassemble Jupiter, Saturn, Neptune, Uranus, and probably throw in all the asteroids and moons for good measure. And even if you somehow gathered that much material, you'd have a new problem: gravity. The sun's gravity would pull on every part of the shell equally, meaning there's no stable configuration. Any tiny perturbation, a meteor impact, thermal expansion, a butterfly flapping its wings in Beijing, would cause the entire structure to collapse inward or drift until it crashed into the sun. It's the engineering equivalent of trying to balance a basketball on top of another basketball for 100 million years. So when Dyson proposed his sphere, he wasn't talking about a solid shell. He was talking about a swarm of independent structures, millions or billions of solar collectors in various orbits around a star. Each collector is probably massive, think kilometers across, covered in photovoltaic materials or heat engines. They're not connected, so if one fails, no big deal. The swarm gradually grows over centuries as the civilization builds more collectors. Eventually, if you build enough of them, you've captured most of the star's output. Cost estimate? Impossible to calculate, but let's try anyway. You'd need to disassemble multiple planets. Mercury is usually the candidate because it's close to the sun, it's made of heavy metals that could be useful for construction, and let's be honest, nobody's going to miss Mercury. Mercury has a mass of 3.3 times 10 to the 23rd kilograms. If you turned all of that into solar collectors, impossibly efficient conversion, ignoring all the rockets and robots and infrastructure, you might capture, say, 10% of the sun's energy. Want to capture more? Start disassembling Venus or Mars or Earth. No big deal, just casually destroying planets to build a megaswarm. The Dyson bubble is a variant where the collectors use solar radiation pressure to stay aloft. Instead of orbiting, they're essentially hovering, balanced between the sun's gravity pulling them in and the sun's light pushing them out. This is statite technology, and it's theoretically possible, but requires collectors so thin and light they'd be measured in atoms. We're talking about structures that make tissue paper look dense. The advantage? You can position them anywhere you want. The disadvantage? They're so fragile that a micrometeorite could shred them. The Dyson shell, the solid shell from science fiction, is physically impossible because of the reasons I mentioned. But that doesn't stop people from talking about it because, let's face it, a solid shell is cooler conceptually. Science fiction authors love it, engineers hate it, physics forbids it. And then there's the absolutely bonkers variant, the Dyson net. Imagine taking a Dyson swarm and connecting all the collectors with cables or beams, not a solid shell, but a rigid structure. This combines the worst aspects of both designs. It's mechanically unstable like the shell, but requires even more material because now you need structural supports. The only reason to do this is if you want your megastructure to also be a habitat with artificial gravity from rotation. Which brings us to the real question. Why would anyone build this? The obvious answer is energy. A Dyson sphere level of energy is a civilization that can do basically anything. Want to run a planetary computer simulation with every atom accounted for? Sure. Want to accelerate a spacecraft to 10% light speed? Easy. Want to terraform every planet in your solar system and build rotating habitats the size of continents? Go nuts. Dyson sphere energy means post-scarcity. It means you've graduated from worrying about electricity bills to worrying about what to do with essentially infinite power. But there's a darker possibility, and we'll come back to this later. Maybe you don't build a Dyson sphere because you want to. Maybe you build one because you have to, because your civilization is growing exponentially, consuming more and more energy, and eventually you either expand to new stars or you suffocate on your own success. Or, just maybe, you build a Dyson sphere because someone else already has one, and you're in an arms race you can't afford to lose. But before we get too deep into speculation, let's talk about something more concrete, the Kardashev Scale. Because if Dyson spheres represent a certain level of technological advancement, we need a framework to understand what that level looks like. And trust me, once you understand the Kardashev scale, you'll realize just how terrifyingly far we have to go and how incomprehensibly powerful a Dyson sphere building civilization would be.
In 1964, Soviet astronomer Nikolai Kardashev had a problem. He was working on SETI, the search for extraterrestrial intelligence, and he realized that saying advanced civilization was meaningless without a benchmark. Advanced compared to what? Us? Ants? Gods? So Kardashev did what scientists do. He created a scale, not based on culture or philosophy or technology in general, but on something measurable: energy consumption. Specifically, he proposed 3 types of civilizations based on how much energy they could harness and use. Type 1, a civilization that can harness and utilize all the energy available on its home planet. That includes solar energy hitting the planet, geothermal energy, tidal energy, everything. We're talking about 10 to the 16 to 10 to the 17 watts of power. Type 2, a civilization that can harness and utilize all the energy output of its home star. This is Dyson sphere territory, about 10 to the 26th watts for a sun-like star. Type 3, a civilization that can harness and utilize all the energy output of its home galaxy. We're talking about capturing the energy from billions of stars, about 10 to the 36th watts. Clean, simple, terrifying. Because here's the thing, on the Kardashev scale, humanity isn't even type 1. We're type 0.73. We're not even a full civilization yet by this metric. We're planetary toddlers playing with fossil fuels and fission reactors, nowhere close to harnessing all of Earth's available energy. Carl Sagan later refined the scale to include decimal points, because going from type 0 to type 1 is such an enormous leap that it's useful to track progress incrementally. Each 0.1 increase represents about a 10x increase in energy consumption. We're at 0.73 and climbing slowly. Every year we consume more energy, currently about 18 terawatts globally. To reach type 1, we'd need to increase that to about 10 petawatts. That's a 500x increase. How long will that take? Optimistic estimates say maybe 100 to 200 years if we transition to fusion and build massive solar infrastructure. Pessimistic estimates say never, because we'll wipe ourselves out with climate change or nuclear war before we get there. Cheerful thought. But let's say we make it to type 1. We've covered the planet with solar panels, fusion reactors, space-based solar collectors beaming energy down to the surface. We've harnessed geothermal from the Earth's core. We're pulling energy from hurricanes and ocean currents. We've done it. We're type 1. Now we look up at the sun and realize our star produces 20,000 times more energy than we're using. All that power just radiating into space. Wasted. So we start building. First, a few solar collectors in close orbit, then more. Then we start mining Mercury for raw materials. Maybe we build a space elevator to make it easier to lift materials from Earth. Maybe we use self-replicating robots, von Neumann machines, to exponentially accelerate construction. After a few centuries of focused effort, we've done it. A Dyson swarm. We're type 2. The jump from type 1 to type 2 is a billion times increase in energy consumption.
1 billion. We went from harnessing one planet to harnessing one star. And here's where it gets psychologically difficult to grasp. The jump from Type 2 to Type 3 is another billion times increase. You go from harnessing one star to harnessing every star in the galaxy. 200 billion Dyson spheres, every star system wrapped, every star harvested. A Type 3 civilization doesn't conquer the galaxy in the Star Wars sense, with empires and planets and trade routes. A Type 3 civilization mines the galaxy. They disassemble planets like Lego sets. They treat stars as power plants. They build structures so vast that they're visible across intergalactic distances. And here's the part that should make you deeply uncomfortable. If a Type 3 civilization exists in our galaxy, they already know we're here. They would have detected our radio signals 70 years ago. They would have seen our cities light up at night. They would have noticed the chemical composition of Earth's atmosphere change from industrial pollution. They know about us, and they're choosing not to respond. Why? We'll come back to that question. But first, let me paint a picture of what each civilization type might actually look like, because these aren't just numbers, these are implications. A Type 1 civilization has complete control over its planet. Weather modification? Trivial. Earthquakes? Preventable. Asteroid impacts? Deflectable. They've probably built space elevators, orbital habitats, moon bases. They've achieved fusion energy, maybe even started experimenting with antimatter. Their computational power is staggering. We're talking planet-scale AI, maybe even digital consciousness. Death might be optional if they've achieved brain uploading or life extension. They're unified or nearly unified politically because squabbling nation-states can't coordinate the kind of infrastructure needed for Type 1 status. War is economically pointless when energy is abundant. Scarcity has been solved, at least materially. And they're looking outward, thinking, what's next? A Type 2 civilization has moved beyond their planet entirely. They probably don't live on planets anymore. Why would you? Planets are gravity wells, resource poor compared to the raw materials floating in space, and vulnerable to all sorts of disasters. No, Type 2 civilizations live in rotating habitats, O'Neill cylinders, Stanford tori, McKendree cylinders, artificial worlds built from asteroid material and powered by the Dyson swarm. They might have billions or trillions of inhabitants living in comfortable artificial environments scattered throughout their solar system. They've achieved something close to immortality through biological or technological means. They're probably running simulations of entire universes inside computer systems powered by a fraction of the Dyson swarm's output. And they're building slower-than-light starships to send out to nearby systems, because even with a Dyson sphere, you eventually want more stars, more energy, more space. They're thinking, how do we replicate this across the galaxy? A Type 3 civilization has done exactly that. They've spread across the galaxy like a wave, building Dyson spheres around every suitable star. They might have trillions of inhabitants, or they might be a single galaxy-spanning consciousness, a hive mind using stars as neurons in a brain the size of the Milky Way. They can move stars if they want to. Stellar engineering, using directed energy to alter a star's trajectory, is trivial to them. They're rearranging the galaxy like furniture. They're not fighting wars. What would they fight over? They control the energy output of billions of stars. Instead, they're probably focused on things we can't even imagine, manipulating space-time, building wormholes, preventing the heat death of the universe, running ancestor simulations. Or, terrifying thought, they're hiding, deliberately, because something out there is dangerous and the smart civilizations keep quiet. But we're getting ahead of ourselves. The Kardashev Scale, as useful as it is, has some weird implications. The first, it assumes unlimited growth. Every civilization progresses from Type 0 to 1 to 2 to 3, consuming more and more energy forever. But what if that's not true? Maybe Type 1 is enough. Maybe once you've solved scarcity and death, you don't need to build Dyson spheres.
Maybe you're happy running virtual worlds with the energy you have. Or, and this is where the great filter comes in, maybe most civilizations don't make it to Type 2. Maybe something kills them before they get there. The great filter is a proposed solution to the Fermi Paradox. If the universe is so big and so old, where is everybody? Why don't we see any evidence of advanced civilizations? One answer, the filter. Something, maybe nuclear war, maybe climate collapse, maybe rogue AI, maybe something we haven't encountered yet, wipes out civilizations before they can spread to the stars. The question is the filter behind us or ahead of us? If it's behind us, if the hard step is abiogenesis, or multicellular life, or intelligence, then we're golden. We're rare, but we've passed the test. We'll probably make it to Type 1 and beyond. But if the filter is ahead of us, if every civilization self-destructs right around 0.7, right where we are now, then we're doomed. We're living in the most dangerous period in human history, and we don't even know what's going to kill us. And finding a Dyson sphere would tell us which side of the filter we're on. If we detect a Dyson sphere, it means at least one civilization made it to Type 2. It means the filter is probably behind us. It means we have a future. Or it means the filter is ahead of us, and that civilization is what happens when you pass it, and they've been silent for millions of years because something happened to them too. Cheerful thoughts, brought to you by the Kardashev Scale. Now, let's talk about whether we've actually found any of these things, because the galaxy is big, and Dyson spheres, if they exist, are hiding in plain sight.
Let's return to where we started. Tabby star, KIC 8462852, the star that launched a million headlines about alien megastructures and made astronomers deeply uncomfortable. Because here's the thing, scientists hate saying, "We don't know." We especially hate saying, "We don't know," and aliens is one of the possibilities we can't rule out. But with Tabby star, that's exactly where we ended up. Let me set the scene again, with more detail this time. The Kepler Space Telescope was launched in 2009 with one job: find exoplanets. It did this by staring at 150,000 stars continuously for 4 years, measuring their brightness with ridiculous precision. When a planet passes in front of its star, a transit, the star dims slightly. Big planets like Jupiter might dim the star by 1%. Earth-sized planets, about 0.01%. Kepler detected thousands of exoplanets this way: routine, predictable, boring. And then there was KIC 8462852. In 2015, a team of citizen scientists, people volunteering their time to analyze Kepler data through a project called Planet Hunters, flagged this star as unusual. The light curve looked wrong, really wrong. First dimming event, 15%. Second, 22%. No periodicity, no regularity, just random, massive dips in brightness. Dr. Tabitha Boyajian, Tabby for short, took a closer look. Her team ran through every natural explanation they could think of. Hypothesis 1, exoplanet transits. Nope. Even Jupiter only blocks about 1%. You'd need a planet 50 times the diameter of Jupiter. That's not a planet, that's a star. And if it were a star, Tabby star would be a binary system, which we'd detect from its spectrum. It's not. Hypothesis 2, multiple planets in alignment. Maybe a bunch of planets all lined up at once. Except that would require an incredibly specific, unlikely orbital configuration, and you'd see them transit regularly. These dips are random. Hypothesis 3, circumstellar disk. Maybe the star is young and still has a debris disk around it. Except Tabby star is an F-type main sequence star, mature, stable, billions of years old. It shouldn't have a disk. Hypothesis 4, asteroid belt or planetary collision. Maybe we're watching the aftermath of two planets smashing together, creating a cloud of debris.
This one had promise, except there's no infrared excess, no sign of the dust we'd expect from fresh debris. Hypothesis 5. Comets. This became the leading natural explanation. Maybe a family of comets on elongated orbits is periodically passing in front of the star, trailing dust and debris. It's possible. Unlikely, but possible. The problem? You'd need an absolutely massive swarm of comets, like thousands of them, each trailing enormous tails, and they'd have to be on very specific orbits to cause the irregular dimming pattern. And we've never seen anything like this around any other star. By 2016, Boyajian and her team published their paper in monthly notices of the Royal Astronomical Society. The title? Planet Hunters 9, KIC 8462852. Where's the flux? And buried in that paper, in the section discussing possible explanations, they mentioned the unmentionable. Although unlikely, we note that the observed phenomenology is consistent with a Dyson swarm or a partially constructed megastructure. That phrase, Dyson swarm, launched a media firestorm. Suddenly, everyone was talking about alien megastructures. The Breakthrough Listen initiative, funded by Yuri Milner to the tune of $100 million, pointed their radio telescopes at Tabby star to see if they could detect any artificial signals. They found nothing. But the mystery deepened, because when astronomers went back and looked at archival data, photographic plates from the 1890s through the 1980s, they found something weird. Tabby's star had dimmed overall by about 20% over the past century. Wait, what? Stars don't dim by 20% over a century, not unless something is fundamentally wrong with them, like they're dying, which Tabby's star isn't, or unless something is in the way, something big. Now, here's where I need to be honest with you. The alien megastructure hypothesis is almost certainly wrong. Not impossible, but very, very unlikely. In 2018, additional observations ruled out opaque objects blocking the star. The dimming is wavelength dependent. Blue light dims more than red light. That's consistent with dust, not solid megastructures. The current leading explanation is a massive cloud of fine dust particles orbiting the star in a complex configuration. Maybe from a destroyed comet, maybe from a planet-sized collision millions of years ago. We don't know. But the fact that alien megastructure was ever on the table in a peer-reviewed paper by serious astronomers tells you something important. We don't have good natural explanations for everything we see. And Tabby star isn't alone. In 2018, astronomers identified another star, EPIC 204376071, with similar bizarre dimming patterns. Then VVVVWIT07, which dimmed by 80% for no obvious reason. Then more candidates from surveys like TESS and Gaia. Some of these have natural explanations, some don't, yet. But here's the key question. How would we actually detect a Dyson sphere? There are three main approaches. Method 1, the Dyson Sphere Detection Infrared Survey. Remember, Dyson spheres absorb visible light and re-emit it as infrared, so we look for stars that are too dim in optical wavelengths but too bright in mid-infrared. The ideal Dyson sphere candidate would be invisible in visible light but blazing in mid-infrared. NASA's Wide Field Infrared Survey Explorer mission cataloged the entire sky in infrared. In 2015, researchers Jason Wright, Matthew Griffith, and others analyzed WISE data looking for Dyson sphere candidates. They found about 50 galaxies and one star with unusual infrared signatures. The star? Nothing conclusive. The galaxies? Probably just heavily dust-obscured galaxies, not Type 3 civilizations. Still, they looked, and they'll keep looking. Method 2, look for transit anomalies. This is what caught Tabby's star. If a Dyson swarm is partially constructed, you'd see irregular dimming as the collectors move in front of the star. The dimming would be chaotic, not periodic like planets. The challenge? Most stars don't have objects transiting from our perspective.
We need to monitor millions of stars to catch the few that might show megastructure transits. Method 3. Look for laser signatures. Some researchers have proposed that advanced civilizations might use powerful lasers for communication or for pushing light sails. If you're running a Dyson sphere, you have the energy to run lasers that would be detectable across interstellar distances. Harvard astronomer Avi Loeb, yes, the same guy who claimed Oumuamua might be an alien probe, has been searching for laser signatures from nearby star systems. So far, nothing. But absence of evidence isn't evidence of absence. Maybe they're not using lasers. Maybe they are, but not pointed at us. Maybe they went extinct before we started looking. Or maybe, most likely, Dyson spheres are just rare. Maybe most civilizations never build them. Which brings us to one of the strangest candidates of all, the possibility that we're not looking for active, functioning Dyson spheres. We might be looking for dead ones. In 2017, the interstellar object Oumuamua passed through our solar system, cigar-shaped, tumbling, accelerating away from the sun in a way that couldn't be explained by gravity alone. The natural explanation, it's outgassing like a comet, producing a tiny thrust, except we didn't detect any outgassing, no coma, no tail, nothing.
Avi Loeb suggested, controversially, that it might be a light sail, a thin artificial sheet designed to be pushed by starlight. Maybe a defunct probe from an alien civilization. Maybe even debris from a Dyson swarm that fragmented millions of years ago. Most astronomers think Loeb is wrong. They think Oumuamua is a weird comet made of nitrogen ice or frozen hydrogen that evaporated in ways we didn't detect. But the point stands. If civilizations have been building megastructures for millions of years, some of those structures probably failed. Some probably broke apart. Debris from dead Dyson spheres might be floating through the galaxy right now, fragments of technologies we barely understand. And if we ever capture one, if a piece of alien megastructure ever falls to Earth, it would be the most important archaeological find in human history. Now, you might be wondering, if Dyson spheres are so useful, why haven't we detected any obvious ones? Why isn't the galaxy full of infrared bright Type 2 civilizations? That's the Fermi Paradox, and it's the question that keeps SETI researchers awake at night. Where is everybody? Let's run through the possibilities. Possibility 1. They don't exist. We're alone in the galaxy. Abiogenesis is so rare, or intelligence is so rare, or technological civilization is so rare that we're the first. Statistically unlikely given the galaxy's size and age, but possible. Possibility 2. They exist, but haven't built Dyson spheres. Maybe Type 2 civilizations are uncommon. Maybe most species plateau at Type 1, satisfied with planetary energy and virtual worlds. Maybe building a Dyson sphere is economically or culturally unappealing. Possibility 3. They exist, but we can't see them. Maybe Dyson spheres radiate in spectrums we're not looking at. Maybe they're cloaked somehow, though thermodynamics makes true invisibility difficult. Maybe they're not around sun-like stars. Maybe they prefer red dwarfs, which are harder to observe. Possibility 4. They existed, but they're gone. Maybe the galaxy was full of Type 2 civilizations millions of years ago, but they all died. Self-destruction, natural disasters, heat death of their suns. We're looking at a galaxy of ruins. Possibility 5. They exist, and they're hiding. This is the dark forest hypothesis from Leo Cixin's novel. Maybe the galaxy is dangerous. Maybe there's something out there that destroys civilizations that advertise their presence. So smart civilizations build Dyson spheres but hide them. Maybe they use the energy output to power cloaking systems, or they build deep inside dense nebulae where we can't see. Maybe, terrifying thought, they're hiding from us. Or maybe they're hiding from something else, something worse. Let's take a break from speculation and talk about something concrete. What are we actually doing to search for these things?
Right now, as you're watching this, there are telescopes pointed at the sky specifically looking for alien megastructures.
Not as a side project, not as a joke, as a legitimate scientific endeavor with funding and peer-reviewed publications. Let me introduce you to some of the key projects. Glimpsing Heat from Alien Technologies, GHAT. This is led by Dr. Jason Wright at Penn State. The project analyzes data from WISE and other infrared surveys, looking for galaxies that are too bright in mid-infrared. The idea, maybe we're not advanced enough to detect individual Dyson spheres, but if a Type 3 civilization has wrapped every star in a galaxy, we'd see the whole galaxy glowing in infrared. They've analyzed about 100,000 galaxies so far, found 50 candidates with unusual infrared excess, but follow-up studies suggest they're probably just dust-obscured galaxies, galaxies going through intense star formation, shrouded in dust. Probably. Hephaestus Project, named after the Greek god of blacksmiths and craftsmen. This project is using Gaia spacecraft dated to look for partial Dyson spheres, stars that are dimmer in optical wavelengths than they should be, suggesting something is blocking some of the light. In 2024, they released a paper identifying 7 M-dwarf stars that showed potential signs of partial Dyson spheres. 7. Not conclusive, but interesting enough to warrant follow-up observations. SETI searches. The Breakthrough Listen initiative is spending $100 million over 10 years to search for technosignatures. That includes Dyson spheres. They're using radio and optical telescopes to scan millions of stars for any sign of artificial signals. They're also looking at weird stars like Tabby's star, checking if they emit radio signals that would indicate artificial activity. So far, nothing definitive. Lots of interesting signals that turned out to be human interference or natural phenomena, but they're still looking. TESS and future surveys. NASA's Transiting Exoplanet Survey Satellite, TESS, is monitoring hundreds of thousands of stars for exoplanet transits, but the same data can be used to search for megastructure transits. Any star showing irregular, massive dimming gets flagged for follow-up. And future missions, like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope, will have even better capabilities to detect anomalies. The point is, we're looking, seriously. And if Dyson spheres exist, we have a realistic chance of finding them in the next few decades. So let's talk about what happens if we do. Imagine this scenario. It's 2031. JWST is analyzing infrared data from a nearby star system, let's say 40 Eridani, about 16 light-years away. The star is an orange K-type dwarf, stable, about 4 billion years old, and the spectrum looks wrong. The star is emitting way less visible light than it should for its mass and age, but it's blazing in mid-infrared. The spectral signature doesn't match any dust or debris we know. The temperature is too uniform, about 300 Kelvin, suspiciously close to what you'd expect from waste heat radiated by technology. Follow-up observations confirm something is absorbing this star's light and re-radiating it as heat. Something big. Something arranged in a complex, ordered structure. The press release goes out. Possible Dyson swarm detected around nearby star. What happens next? First, global pandemonium. This would be the biggest news story in human history. Every government, every space agency, every billionaire with a rocket company would immediately start planning missions. We'd point every radio telescope at 40 Eridani, looking for signals. Every optical telescope would scan for details. Second, scientific revolution. If a Dyson sphere exists 16 light-years away, that civilization has been there for how long? Building a Dyson swarm isn't a decade-long project. It's a millennia-long project, maybe longer. So whatever we're looking at, it's old, really old. Third, existential questions. Because here's the disturbing part. If they're 16 light-years away and they have Dyson sphere-level technology, they almost certainly know we exist. Our radio signals have been leaking into space for 100 years. Those signals have traveled 100 light-years in every direction. 40 Eridani is well within that bubble. They've heard us, and they've chosen not to respond. Why? Theory 1, the zoo hypothesis.
Maybe they're watching us like we watch animals in a wildlife preserve. Non-interference. Let the primitive species develop naturally. Maybe they have a prime directive like in Star Trek, no contact until we achieve certain technological or ethical milestones. Theory 2, we're not interesting. Maybe to a Type 2 civilization, we're like bacteria. Sure, bacteria exist, and maybe they're scientifically interesting, but you don't try to communicate with bacteria. We're too below them. Theory 3, communication is pointless. Maybe they tried sending signals, but we didn't detect them. Or maybe they realized that any conversation would have a 32-year round-trip delay, 16 years for our message to reach them, 16 years for their reply to reach us, and they've decided it's not worth the effort. Theory 4, they're dead. Maybe what we're seeing is a relic. The Dyson swarm was built 1 million years ago, and the civilization that built it collapsed. The structure still orbits the star, still radiates heat, but nobody's home. We're looking at a monument to a dead species. Theory 5, they're hiding. Maybe they know something we don't. Maybe there's a predator species in the galaxy that hunts advanced civilizations. The smart species build Dyson spheres but stay quiet. And us detecting them just announced our presence to something dangerous. That last one should keep you up at night. But let's say we detect a Dyson sphere and we decide to send a message. What do we say? This is where things get philosophically complicated. In 1974, we sent the Arecibo message, a radio signal aimed at the globular cluster M13, 25,000 light-years away. It contained basic information about humanity, our DNA structure, our population, our solar system. It was symbolic, because by the time the signal reaches M13, humanity will probably be unrecognizable. But we sent it anyway. Now imagine we're sending a message to a confirmed Type 2 civilization. What do we say? Hello, we are humans, we are made of carbon, we like oxygen and liquid water. They probably figured that out from our atmospheric composition. We'd like to trade knowledge? What knowledge could we possibly have that a Type 2 civilization doesn't have? We'd like to trade with you? What resources could we possibly offer that a Type 2 civilization couldn't obtain? Please don't kill us? Maybe that's the most honest message. Or maybe we say nothing. Maybe detecting a Dyson sphere is the moment we shut up, turn off all our radio transmissions, and hope they didn't notice us. Because here's the uncomfortable truth. If a Type 2 civilization wanted to destroy us, we couldn't stop them. Think about the power differential. We're Type 0.73. They're Type 2. That's a factor of 1 billion difference in energy consumption. 1 billion. To put that in perspective, imagine a civilization of ants trying to fight modern humanity. That's the ratio. Actually, it's worse than that. Ants to humans is maybe a factor of 1 million. We're talking a factor of 1 billion. A Type 2 civilization could accelerate a projectile to a significant fraction of light speed and throw it at Earth. Relativistic kill vehicle. We'd have no warning. It would arrive moving so fast we couldn't see it coming. The impact would release more energy than every nuclear weapon ever built. And to them, it would be trivial, a rounding error in their energy budget. Or they don't even need to attack us directly. They could just ignore us. And in a few centuries, they'd expand to our solar system, disassemble our planets for raw materials, and we'd be in the way. Sorry, humans, we need your mercury for more Dyson collectors. You understand. This is the dark side of the Dyson sphere search. We're not just looking for neighbors, we're looking for gods. And gods don't negotiate with ants. But maybe I'm being too pessimistic. Maybe a civilization advanced enough to build a Dyson sphere is also advanced enough to have moved beyond resource conflicts. Maybe they're peaceful. Maybe they'd be willing to teach us, uplift us, share their knowledge. Or maybe, most likely, they'd be so different from us that concepts like peaceful or hostile don't even apply. Maybe their goals are so alien that we couldn't comprehend them. Arthur C. Clarke said, "Any sufficiently advanced technology is indistinguishable from magic. A Type 2 civilization's technology would look like magic to us, and not fun magic, terrifying, incomprehensible magic." But here's the flip side. If we find a Dyson sphere, it means the great filter is behind us. It means civilizations can reach Type 2. It means we have a future. Unless, of course, we're in a galaxy full of dead Dyson spheres, monuments to species that built these megastructures and then went extinct anyway. Which brings us to the final question: what if we don't find any Dyson spheres? What if we search for another century and find nothing? That might be the most terrifying answer of all.
Let's talk about silence. We've been broadcasting radio signals into space for about 100 years. Those signals have created a bubble 200 light years across, a sphere containing about 15,000 stars. We've announced our presence to thousands of star systems, and we've heard nothing back. We've been actively searching for extraterrestrial intelligence since 1960. The Drake equation, Project Ozma, the WOW signal, Arecibo, SETI at home, Breakthrough Listen. 65 years of searching. Nothing. We've discovered over 5,000 exoplanets. We know Earth-like planets are common, maybe billions in our galaxy alone. We know organic molecules form easily in space. We know life emerged on Earth surprisingly quickly after the planet cooled. And yet, silence. This is the Fermi Paradox, named after physicist Enrico Fermi, who supposedly asked during a lunch conversation, "Where is everybody?" If life is common, and intelligence is reasonably common, and civilizations last long enough to become spacefaring, then the galaxy should be teeming with signals. We should see Dyson spheres around millions of stars. We should see evidence of mega-engineering projects, stellar manipulation, massive structures. We see none of that. So either, A, we're the first. Somewhere in the galaxy, someone has to be first. Maybe it's us. Maybe we're the elder civilization, the precursors, the ones who will fill the galaxy with life. It's statistically unlikely, but possible. B, intelligent life is rare. Maybe the jump from simple life to complex life is insanely difficult. Maybe the jump from complex life to intelligence is even harder. Maybe tool-using, technology-building civilizations are 1 in a trillion occurrences. C, civilizations self-destruct before becoming spacefaring. This is the great filter hypothesis. Maybe every civilization reaches a bottleneck: nuclear war, climate collapse, rogue AI, bioweapon pandemic, and most of them don't survive. We're currently in that bottleneck. Maybe that's why we don't see anyone. They all died before building Dyson spheres. D, they're hiding. The dark forest hypothesis. Maybe the galaxy is full of civilizations, but they're all staying quiet because broadcasting your presence is suicide. Maybe there's a predator species that hunts advanced civilizations. Maybe the quiet ones survive and the loud ones get eliminated. E, they're here, but we can't see them. Maybe alien civilizations exist, but they're not building Dyson spheres. Maybe they've moved to virtual realities. Maybe they've uploaded themselves into black holes where time runs slower and they can think for trillions of years. Maybe they've transcended physical form entirely. We're looking for megastructures, but they've moved beyond physical construction. F, they don't want to build Dyson spheres. Maybe capturing 100% of a star's energy isn't desirable. Maybe it's environmentally destructive, or culturally repugnant, or just inefficient compared to alternatives we haven't thought of. Maybe advanced civilizations use quantum vacuum energy, or black hole farming, or something we don't have the physics to imagine. Each of these answers has profound implications for humanity's future. If we're the first, we have a responsibility. We're the ones who will seed the galaxy with intelligence. Every decision we make about our future, whether to expand, how to treat other life, what values to uphold, will echo across billions of years. If intelligent life is rare, then we're precious, possibly unique. The universe spent 13.8 billion years producing us, and if we go extinct, it might never happen again. Every human life becomes infinitely valuable because we might be all there is. If civilizations self-destruct, we're in danger right now.
The fact that we haven't detected anyone means the filter is probably ahead of us, and we need to figure out what it is and how to survive it. Nuclear war? Climate collapse? AI alignment failure? We need to be very, very careful. If they're hiding, we should too. Stop broadcasting. Stop building visible megastructures. Keep our heads down and hope the hunters don't notice us. If they've transcended physical form, maybe that's our future too. Maybe building Dyson spheres is a primitive approach, and the real goal is computational substrate optimization and virtual realities and forms of existence we can't currently conceive. And if they just don't want to build Dyson spheres, maybe we shouldn't either. Maybe there's a good reason they don't. Maybe we should think very carefully before we start disassembling Mercury. Here's the thing that gets me. We're searching for Dyson spheres as if they're the pinnacle of achievement, as if capturing a star's energy is the obvious goal of any advanced civilization. But maybe it's not. Maybe Dyson spheres are evolutionary dead ends. Maybe the civilizations that build them get locked into exponential energy consumption, trapped on a treadmill of growth, unable to stop. Maybe they eventually cannibalize their own solar systems, and then they're forced to expand to new stars or collapse. Maybe the smart civilizations never build Dyson spheres. Maybe they stay small, stay sustainable, and survive for billions of years by not overreaching. Or maybe, most disturbing thought, maybe building a Dyson sphere is what attracts the attention of whatever's out there in the dark. Maybe it's a beacon, a signal that says advanced civilization here, come get us. And maybe that's why the galaxy is silent, because the ones who built Dyson spheres are gone and the survivors learned to stay hidden. I don't know which answer is true. Nobody does. But here's what I do know. We're actively searching for these megastructures. We have the technology to detect them if they're out there, and in the next few decades, our surveys will be comprehensive enough that we'll have scanned most of the galaxy's nearby stars. If we find nothing, if we search thoroughly and find 0 Dyson spheres, that tells us something profound about the nature of intelligence and civilization. It means either we're alone, or everyone else chose not to build them, or everyone else is dead. None of those options are comforting. But if we do find one, if we detect an artificial structure around another star, it means we're sharing the universe with minds that have achieved what we're still struggling towards. It means intelligence survives, technology advances, and the future is possible. And it also means we're being watched by something incomprehensibly more advanced than us. And maybe that's the most human thing about this whole search. We're looking for Dyson spheres not because we need to find them, but because we need to know if there's anyone else out there. We need to know if there's anyone else out there who looked at a star and thought, I could capture that. We need to know if our future is written in the sky, or if we're writing it ourselves in real time, with no template, no guidance, no assurance that we won't fail. The search for Dyson spheres is really a search for hope. Hope that intelligence survives. Hope that we have a future beyond this fragile planet. Hope that somewhere in the vast dark, someone else looked up and wondered the same things we're wondering. And if we find nothing, if the galaxy stays silent, then maybe we're the first. Maybe we're the ones who will build the first Dyson sphere, who will become the Type 2 civilization that future species will search for. Maybe the reason we don't see anyone is because they're waiting for us, because we're the ones who will fill the galaxy with life and intelligence and megastructures that blaze in infrared for anyone looking. Or maybe we'll choose differently. Maybe we'll become the hidden civilization, the quiet one, the species that survives by not advertising its presence. Either way, the search continues. Right now, telescopes are scanning the sky. Algorithms are analyzing data, scientists are flagging anomalies, and somewhere out there, maybe 16 light-years away, maybe 1,600 light-years away, there might be a structure so vast it dwarfs our comprehension, built by minds we couldn't understand, powered by energies we're only beginning to harness. Or there might be nothing, just stars and silence. Both possibilities are terrifying. And that's why we keep looking. Thanks for watching. If you want to dive deeper into the Fermi Paradox and why the galaxy's silence might be the most terrifying mystery of all, check out my videos. Until then, look up, wonder, and remember, if we do find a Dyson sphere, everything changes. Everything.